Okay, good afternoon, everybody. Welcome to today's AJS. Thank you all for being here. Today's speaker is Chiara Lonati, postdoc from Politecnico di Torino, and their talk will be about Nematic axysimmetric films, a variational analysis. Please, Chiara, you can start.
Thank you, Roberto, for the introduction, and good afternoon, everyone. And let me thank the organizers for the invitation and the opportunity to talk about my research. As Roberto said, I'm a postdoc at Politecnico di Torino in the field of applied mathematics, and in particular, I'm interested in nonlinear elasticity. And during last year, mainly I'm focusing on porous media homogenization and, let's say, optimization of porous media for cell migration. However, today I would like to present you two research works regarding two variational problems for surfaces made up of nematic liquid crystals that are axisymmetric, so they are revolution surfaces. So I would like to mention that these results were carried out in collaboration with Luca Rossardi from Politecnico di Torino, Alfredo Marzocchi from Università Cattolica del Sacro Cuore in Brescia, and Giulia Bevilacqua, that is since February a researcher at Ca' Foscari in Venezia. So I would like to start with some basic notions to introduce the topic to who's interested, and then some literature results, and then I would like to present you my problems. So just to start, some notions on liquid crystals. As I think you all can imagine, they are materials that lie in an intermediate phase between the solid phase and the liquid phase. So as you can see from this picture, you can see that the solid phase present irregular molecular ordering, while liquid crystal present a partial molecular ordering that is more similar to the one of the solids, with respect that one of the liquids. In particular, however, liquid crystal present also a certain degree of fluidity, so they are partially solid and partially liquid. In particular, they have also some properties that are typical of this phase, such as this one. So they present birefringence, iridescent colors, and they have two melting points, one at 145 Celsius degrees and one at 178 Celsius degrees. So we start from a solid sample, we heat it, and then we arrive to the first melting point. We obtain this milky and opaque substance, and then we heat again, we arrive at the second melting point, and we obtain a transparent substance that is more a liquid in the liquid phase. Now, they were discovered in 1888 by Reinitzer, that was a botanist, that found out that there existed a material that presented two melting points in cholesterol benzoate. And then all his experiments were recovered by Otto Lehmann through optical spectroscopy. However, many scientists did not believe that liquid crystals were a new material, and so they were the first important studies dates just to 1970, so around 50 years ago. However, these materials are really frequent in nature and also in applications. In nature, they can be found, for example, in natural elements or in cell membranes, in protein, and in the DNA. While as regards technological applications, we can find them in lenses, in optical switches, and you can think about your LCD televisions. So we have that liquid crystals can present different phases. In particular, these are the three most common. So we have cholesteric phase, mective phase, and nematic phase. The cholesteric phase, as you can see here, is characterized by the fact that the molecules are stacked in different planes. The longest molecular axis lies in this plane, and all the planes are slightly rotated with respect to one another. In the mectic phase, we have that, again, the molecules are stacked in planes, but the molecular axis is perpendicular to the plane. While in the nematic phase, you can see that there is no more this arrangement in different planes, but you can see that all the molecules have a partial molecular ordering because they tend to align their longest axis along a common direction, in this case vertical. Now, the nematic phase is the one in which we are interested and is the most common phase. In particular, it is characterized by the fact that the molecules are long from 2 to 3 nanometers. And in particular, as you can see here, the molecules tend to align along a common direction. And this common direction is specified by a unit vector n that we will use. And it is called director. and has mainly two properties. The first is the fact that in the nematic phase we do not have polar molecules, so we have added symmetry, and this means that n is equivalent to minus n. So this will be a characteristic that has to be taken into account when we model this kind of substance. On the other side, we also have that in the natural state, in the ground state, n tends to be a uniform vector field, and so its gradient tends to vanish. Now, as regards literature results, there are several theories that can model liquid crystals. In particular, we have, for example, the Q tensor theory, we have Leslie-Erikson one, we have Landau-Desgen. The one, however, that we use is the Ozen-Frank energy, that basically takes into account the energy that is required to take the crystal in the natural state and deform it to the nematic phase. So in particular, it gives us an energy functional that expresses the energy developed by the crystal. This energy depends on n, and you can see that it's integral over a domain, in this case three-dimensional, of an energy density W that depends on n and its gradient. So the first property is the fact that not having polarity, W of minus n minus the gradient of n must be equal to the energy density computed for n and the gradient of n. And then we know that the energy density has this log expression. So it depends on n, its divergence, the rotor, and the gradient. So we have K1, K2, K3, and K4, and K24 that are four constants that can be now any constant. In particular, they have to satisfy these relations that are called Erikson inequalities that guarantee that this energy density is positive. And here you can see we have four terms. In particular, every term represents a different phenomenon that the liquid crystal can undergo. So the first term represents play, the second represents twist, so a torsion in space. Then we have bending, while K24 is a more complicated term that is called Saddle's play, and is mainly a boundary term that frequently vanishes. So in our model and in many works, we use the one constant approximation. That means that K1 is equal to K2 is equal to K3, that are equal to a constant K, that is a nematic constant. Okay. And then K24 is assumed to vanish. So we have just these three terms. When we put this all together with the same constant K, this reduces to 1/2 of K times the square norm of the gradient of n. Okay, so in the literature there are many results about the Ozen-Frank energy. In particular, one usually wants to find equilibrium configurations for the vector field n on fixed surfaces. So for example, a sphere, a cylinder, a torus. And so one wants to minimize this energy functional on a peculiar space. Now here I wrote W12, but a peculiar space with some boundary conditions. In particular, as regards boundary conditions, there are many types of boundary conditions. There is strong anchoring that basically prescribes a particular, for example, angle for n at the boundary. There are conical and weak anchoring that are give more freedom to the attach at the boundary. And then there are also a lot of studies of the interaction of the nematic vector field n with electric and magnetic fields, in particular in the Fredericks transition, for example. And one other important aspect is the study of regularity of solutions, of equilibrium configurations. And this is because there are many possibilities in which there can be singularities of solution. And so you can think, for example, to a sphere and the Hairy-Ball theorem that is an analogous. And in particular, these singularities are called defects, and they're really important. I would like to mention that I'm also working on the study, for example, of how a defect in a cell membrane or tissue membrane in biological scenarios can lead to the formation of tumors or of cancer cells. So, in particular, these results are obtained mainly for fixed surfaces, and n is always considered a vector that is tangent to the surface. And so here, the basic gradient that we consider here is the surface gradient. However, what does surface gradient mean? This is a subject question because there are different options. So the first that was used in many, many works is the covariant derivative. So the surface gradient of n, if computed with the covariant derivative, takes into account the fact that the surface is curved in space. So it is not a flat surface, it is curved in space. However, recently, during the last, let's say, 8 to 6 years, Napoli and Vergori re-examined this theory and computed, for example, this energy with the surface gradient on a cylinder and obtained some results that, with the covariant derivative, were not, for example, observed in experimental results. And so they formulated a new option that is to take into account not just the covariant derivative, but the complete surface gradient. That means taking into account the covariant derivative and this term, that is the square norm of the extrinsic curvature tensor applied to the nematic director. This basically means that we take into account properly the geometry of the surface on which the crystal is lying. So we take into account how this surface is curved in space. And this is because the extrinsic curvature tensor L, basically, at least in our case, that is a revolution surface case, it is a diagonal matrix that has as first and second element of the diagonal the principal curvatures of the surface. So it describes really how the geometry of the surface is in space. So now coming to the two problems that I studied, uh, since there are many results on fixed surfaces, one interesting problem was to study what happens when the surface is not fixed, but it is flexible. So basically, nematic film means that we have a surface that is elastic, so it can be deformable, and that is equipped with liquid crystals that are in the nematic phase. So basically, we have a surface that is not fixed and whose shape can be influenced, affected by the direction of the nematic vector field, and vice versa, the direction of n can be influenced by the shape of the surface. So in particular, we have an energy functional that describes this surface and we want to minimize it, so to find equilibrium configurations that are minimizers of this functional. So as you can see here, we have this energy functional that depends on n and on the surface. That is the integral of the surface, and there is the sum of two terms, so there is a non-trivial competition of two energy terms. The first is gamma times the A, so it is the classical area functional multiplied by the surface tension gamma that tends to minimize the area of the surface. And then the second term is the Frank energy computed just with the covariant derivative, so just with the first part that I was telling before. So in particular, you can see that the surface acts not just in the integral, but also in the fact that the covariant derivative is computed on the surface. So we assume that to work with revolution surfaces, so our surface will have a profile ρ, and at the boundary we'll attach to this configuration. So we have two circles in space that are coaxial, they are parallel, they have radius r, and they have distance 2h. So in particular, we can rewrite our energy functional using this variable ρ, and using c. C will be the ratio between k and 2 gamma. And so basically it tells us which term prevails on the other. So in particular, when c tends to infinity, we know that the nematic prevails on the area part. In particular, there are two works in which a problem similar to this was studied, one by Giomi in 2018 and one by Napoli and Vergori in 2018. Now, Giomi mainly studies the same problem but with different techniques, with mainly more differential geometry approach. And Napoli and Vergori use some numerical approach, and they do not really study the minima, but just the critical points of the functional. So they just derive Euler-Lagrange equation and see how the solution of the Euler-Lagrange equation behave. Now, the main difference between the two works is the fact that in the first work, just the covariant derivative is considered, while in the second work we have also the presence of the extrinsic curvature term. And we will see that different assumptions on the surface gradient of the surface lead to completely different results in terms of the shape of the surface. So for this first problem with just the covariant derivative, to obtain the functional, so to rewrite it and pass from the first formula to the second, We parameterize our surface as a revolution surface, a standard way. And then we can rewrite, we can decompose our direct vector field n in this way. So EP is the direction of the parallel, EM is the direction of the meridian, and alpha is the convex angle between the parallel and n. Why is alpha convex? Alpha is in 0 pi because we know that there is a tail symmetry, and so n is equivalent to minus n, and we can choose alpha to be just in 0 pi. So with all this substitution into the functional, we obtain this long formula. So this is a complete functional that is quite different from the one that I was showing before. And this is because the first line, apart from the constant 2 pi gamma, is precisely what we are going to study, because k over 2 gamma is precisely c, and so it is this functional that we want to minimize. The other three lines are negligible. Why? So the fourth line is negligible because when we integrate this part, so the integral from 0 to 2 pi of alpha derived with respect to phi in d phi, we obtain alpha in 2 pi minus alpha in 0, but we know that n is smooth, and so this vanishes. The other two lines, you can see that they are just positive terms, and so we know that the functional is already minimized when these two terms go to 0. And however, you can see that they can go to 0 when alpha is constant with respect to phi and with respect to x. So we know that to minimize this functional, we can choose alpha constant. So this means that the angle here between n and the parallel is always a constant angle across all the points of the surface. So this is not, this is a subtle thing in the first place, because then in the functional I want to study, we do not see really the inclination of n with respect to the parallel. And so having a constant angle across all the points can be assumed just because we are not imposing boundary conditions for n at the boundary, so at the two circles, because for example, if we assume here that n is horizontal and that here n is vertical, so along the meridian, it is clear that we cannot choose a constant angle alpha, and the angle alpha has to change across the surface, across the parallels. So here we proceed without boundary conditions, so we can assume that alpha is constant, can be any constant, and so we just want to minimize this first functional. So this is C. So the first thing that we did was to study what happens when C is equal to 0. So when C is equal to 0, we have that this part vanishes, in particular the nematic part vanishes, and we have just the classical area functional. So this means that the problem reduces to the classical plateau problem that has as boundary the two circles that have distance 2h, they have radius r. So basically, we know from classical results that when C is equal to 0, so we have the plateau problem, the minimizer for the plateau problem depends on the aspect ratio h over r, so 1/2 of the distance between the plates and the radius. So we know that if h over r is less than omega, that is this value, the unique minimizer is the catenoid, and the profile of the catenoid is a catenary that we will denote by rho 0, that has this expression, where in particular we have this hyperbolic sign, and pi 0 is a positive quantity and is the largest solution of this equation. This equation is a transcendental equation that basically translates the boundary conditions. And in particular, it is also classically known that when we solve this equation, we have two solutions, so we have two catenary, one will be unstable and one will be stable, and this is precisely this one. On the other side, if h over r is greater than omega, we know that the unique minimizer are the two disks, so the Giomi solution, even if the catenary it still exists, because it exists just when h over r is less than 0.668. So the first thing we did was to prove again all these classical results, in particular on this space. So we have rho W11, rho strictly positive, and the boundary conditions. And we did this partially following some results by Greg. So once this was done, we have the mean result. So if h over r is less than omega, so this means that the unique minimizer for the plateau problem is a catenary, Then for every C, we have at least a minimizer. And this minimizer has a lot of geometric properties that are the fact that it's C2, even strictly convex. It always lies between the catenary, so it is higher than the catenary, but it always lies under the straight segment at height R. We have that it tends to the straight segment as C tends to infinity. We have that this minimizer satisfies this Euler-Lagrange equation, and there's this first integral that basically is the height of the intersection between the vertical axis at x equal to 0 and the minimizer. All these results were achieved in this paper that was recently published. So I just would like to say some just a remarks on the proof. As a space, we worked in the space that I was saying before, so W11. And there are mainly two remarkable things. The first is the fact that the energy decreases by convexification. So as you can see here, if we work, for example, with piecewise affine functions, we take a piecewise affine function ρ1 and its convex envelope ρ2. We can see that the energy developed by ρ1 is greater than the energy developed by ρ2, and so it is energetically convenient for the eventual minimizer to be a convex function, because in general the convex envelope of a function develops less energy. And so this tells us that the eventual minimizer will be a convex function, so it will always lie under the straight segment at IR. And moreover, this holds not just for all the functionals, so not just all the energy terms, but for both energy terms taken one and the other after. The second thing is that also we can prove by contradiction that it is energetically convenient for the minimizer to be above the catenary. So by contradiction, for example, if we take here an arc of rho that lies under the catenary ρ0 in blue, then we can prove by contradiction that it is energetically convenient to lie above the catenary because we develop less energy staying above the catenary. And so we have, let's say, controls on the function and on its derivative because we know that derivatives of r and of ρ0 are bounded at the boundary x plus or minus I, h, and then one can use this direct method of calculus of variations to prove that there exists at least the minimizer. So we then carried out some numerical simulations to validate our results. So as you can see here, we have two-dimensional representation. So you can see that the minimizer is always between the catenary in blue and the straight segment. It tends to the straight segment as C tends to infinity, so as the nematic tend to prevail and the area term tend to vanish. It is an even function. And you can see that also in the three-dimensional representations, our revolution surface is larger than the classical catenoid. One thing that we could not prove is the fact that this intersection here, this height, that is the first integral, increases with C. And this is probably due to the fact that the Euler-Lagrange equation is not explicitly integrable, so we do not have an explicit expression for the minimizer. And so we could basically not prove that this is increasing. That is instead a thing that can be seen through numerical simulations. So in particular, some further developments on this first problem are the fact that one could try to minimize a functional without the one constant approximation. So using K1, K2, K3, maybe letting K24 vanish. And the other thing would be interesting to consider what happens when we put boundary conditions. So, for example, alpha equal to 0 in one of the two circles and alpha, for example, equal to 1 half of pi, so a vertical orientation of n on the other circle. So to see what happens when the nematic director has to change along different parallels. As regards instead the second problem, we decided to take into account also the extrinsic part. So this is the functional that was taken into account in the paper by Napoli and Vergori. So we just have the area functional as before, and then here we have the complete surface gradient. So we have the covariant derivative part and the extrinsic curvature part. So we use the same setting as before. So we have the two circles that are coaxial parallel. We consider again revolution surfaces. And then we rewrite all the functional with the substitutions as before. And again, we have these three lines of functional. In particular, we are mainly interested in minimizing this first line. And this is because clearly it is more affordable to try to choose an alpha that is constant. But here the presence of cosine squared and sine squared is, let's say, gives a complicated functional. Because, for example, if the sine is different from zero, then we have also the second derivative of rho. So the first choice that we chose to apply was to choose alpha equal to zero. And this is because in the paper by Napoli and Vergori, they did choose two choices. The first was to try alpha equal to zero. So the nematic director is always horizontal, so it lies along the parallels. While the second choice was to put alpha equal to 1 half of pi, so the nematic is always vertical, so it is always along the meridians. However, already Napoli and Vergori observed that with alpha equal to 1 half of pi, so always a vertical orientation of the nematic, it is quite difficult to carry out some theoretical considerations, and just for the moment, numerical simulation seem to be useful. So we decided to choose alpha equal to 0. So basically, this is 0, and this is 1. So putting all together, calling this C, the functional that we obtain is this one. So we have a part that is just in rho prime, a part that is just in rho with the presence of C. So we decide to work in the same space as before, because we have linear growth here in rho prime. And then this is our main result. So again, we work in the setting where each over R is less than omega. And we have that for every C, there exists a unique minimizer. So this time we have uniqueness of the minimizer. And we have this complete characterization. So basically the shape strongly depends on the value of C. And this, as you can see, considering the extrinsic part, leads to completely different results from the other work. So if C is less than R squared, we have this explicit form of the minimizer. And in particular, this E is the first integral, and is, in this case, has to be greater than pi 0. And this E is the unique solution of this that is greater than pi 0. If C is equal to R squared, then the unique minimizer is the straight segment at R, so the revolution surface is a cylinder. And on the other side, if C is greater than R squared, then we have this explicit form. You can see that is quite analogous to this. In this case, E is a unique solution of this equation that is positive. And all these results are inside in this paper that is a preprint since January. So we can also say other things on the characterization of this minimizer. We have this Euler-Lagrange equation that can be integrated differently from before. Indeed, we obtain the explicit form of the minimizers. Then we have this first integral. So you can see that if C is equal to 0, we recover the first integral said before. So the height of the intersection between the minimizer and the vertical axis. And however, if C is different from 0, we have this more complicated expression. And then we have also this characterization. So in the first case, when C is less than R squared, the minimizer is infinity, it is even as strictly convex. So it is similar to the case treated before. If C is greater than R squared, we have that it is even and strictly concave. It always lies between the catenary and under this function. And this function is basically an arc of circle, and it is basically the limit when C tends to infinity, so when the nematic prevails. So before it was a straight segment, now it is a concave arc of circle. We have also that the minimizer increase with C, and then we have that the minimizer, as I was saying before, tends to this arc of circle when C tends to infinity. So here we did some numerical simulations as before, so we give the Euler-Lagrange equation, we numerically solve it, and then we plot the solutions. So they are precisely respect our results, so they are even, they increase with C. This is the case when C is equal to R squared. As you can see here, we have the cylinder. It is similar to the cases before, so it is convex when C is less than R squared. Here we have the catenary. And then if C is greater than R squared, we have all these concave solutions. So we have this red profile. And then when C tends to infinity, we have this black curve. So one of the main differences with the preceding work was the fact that we have uniqueness, and this was quite difficult to obtain. In the work by Napoli and Vergori, they just observed that there can be many solutions, multiple solutions, so multiple critical points for the functional when gamma is small, and here instead we proved analytically that there is just one minimizer. Indeed, if we go back here, you can see that there are these equations. So when you solve these, you can have different values for the first integral, and the first integral determines your rho c in 0. So in particular, when gamma is small, so we are in the first case, gamma is the adimensionalized version of C. Here we can have one, two, or three solutions, while here in the second case there is just really one positive solution, so we do not have doubts on the uniqueness of the minimizer. So in particular, if C is greater than R squared, we have a sort of we have this curve, let's say. So you can see that the intersection, once C is fixed, or gamma is fixed, you can see that this curve has a unique intersection point between and with any vertical line that basically represent the aspect ratio of our problem. So we have a unique minimizer. On the other side, you can see that all these color curves, when we cross them with when an horizontal line, we can have one, two, for example, and three solutions. So we have basically three critical points. So if we start from the case gamma equal to 0, this means that we have C is equal to 0, that is the classical plateau problem. So you can see we have this blue function. And you can see that if we have an horizontal line, so for different aspect ratios, we have always two intersections. And basically they are the unstable catenary and the stable catenary. So basically this is our capital pi 0. Well, let's say this curve from here to here represents our capital pi 0. So if we take, for example, gamma small, in particular gamma between 0 and this gamma star that is 0.0257, so really a small range of gamma, you can see that we can have more than one intersection, for example, here. So these will be two unstable critical points, and indeed they lie under the unstable catenary. On the other side, we can prove that there is a unique intersection here that will be will be above the stable catenary, and this tells us that there will be a unique minimizer. So the proof is quite difficult. The unique simple case is when gamma is, let's say, greater than gamma star, because here we have decreasing function, so we can just prove that the derivative is negative. While here it is really difficult to characterize, so we have to study inflection points and we have transcendental equations, so quite difficult to study, but we can prove that here, for example, the function is always concave and there is a unique intersection points that lie above pi 0, and so a unique minimizer. So as regards instead the proof of existence, we use the theorem by Botterone and Marcellini in this work. So we relax the function, in particular the boundary conditions. We prove through their theorem that there is a minimizer rho c, guaranteeing that it is energetically convenient for our eventual minimizer to stay above a strictly positive constant that in particular is related to the classical catenary. So we have a bound from below. Then we prove that this minimizer rho c for the relaxed functional satisfy the boundary conditions. So basically it is not just a minimizer for the relaxed functional, but also for the initial functional. Then we prove that it is convenient, as in, let's say, as in the previous case, to prove that the minimizer will stay above the catenary and under the circle, the arc of circle, that is rho infinity. And finally, we have a minimizer with its regularity, that is the minimizer for the original functional, not relaxed, and then one can integrate the Euler-Lagrange equation and carry out all the study, the work about the geometric characterization and the uniqueness of the minimizer. So interesting further works in this perspective would be to study, for example, what happens when alpha is equal to 1 alpha pi, because again, the functional seems difficult to treat. And in general, for any orientation, because the function is not coercive, so it is not a simple problem. And another interesting thing would be to study what happens when h over r is greater than omega, because we always studied the cases where h over r is less than omega because we needed a bound from below, so we needed the presence of the catenary. So what happens when the minimizer for the plateau problem are the two disks? So analytical still we don't know. We think that the presence of the nematic part would regularize the solution, and that there cannot be an analogous of the Giomi solution for some kind of for this kind of problem. So if we had the nematic, probably we do not have we do not lose regularity, for example, as in the Goldsmith case. And so this was all I wanted to say. And so I thank you for your attention.
Thank you, Chiara. Thank you very much. Are there questions from the room or online? If not, I may ask something. You hear me, yes?
Yes.
Yes.
I was wondering something relating both, I guess, mathematics and physics, but maybe my physical question are just because I don't know so much about mathematics. So I was wondering if you change temperature, you just change the constants K1, K2, K3, K4 you have, or something different can happen?
Okay, so I'm not an expert too in pneumatics.
Okay.
There are different kind of pneumatics that can be driven by concentration, by temperature. So it's not really simple. Yes, I think that if you change the temperature, you just have to change. Where is it? What is it? Okay. Yes, you probably have to change this K1, K2, K3, K24, I think, because this could drive for different phenomena. So I think you have just to take into account this here.
Mm-hmm.
Or if you want to add another, let's say, boundary term or another term in the energy functional.
Okay. And the fact that there is no polarity in these nematics, I would say, is it also, I mean, physical because it's what happens, or it's just some simplification that you made to have such energy that is in a way simplified and that you can treat?
No, as far as I know, it is observed that they have
Okay.
no polarity, and so
Okay.
this is a good approximation. This is a
Mm-hmm.
good property.
Mm-hmm. Okay. Perfect. I see that Davide raised a hand. Please, Davide.
Yes, thank you. Thank you very much, Chiara. And I have a curiosity, maybe related to the one of Roberto. So, this is a model for nematic liquid crystals. So, for example, in the case of smectic liquid crystals, how does the energy change? So, do you have any
Uh,
idea? And maybe also what
um,
can drive this kind of transition?
Okay, so I think that when you have smectic crystals or other type of crystals, you have basically different base phenomena, such as this one. So I think the Frank energy can be changed, taking into account the basic deformations that there's, for example, smectic crystals can undergo. So I think it's an analogous of this energy with maybe not KH4, so just some terms of this energy. So you have, so it depends on the basic deformation that you can this type of crystal can undergo, basically. And so
Okay.
this would be another interesting thing because you should not consider probably the one cost approximation. So there is a base difference here. So probably the energy here surely is really more complicated because you don't have this approximation.
Okay, thank you.
And Chiara, what about if you change the condition to your surface to be attached to these two circles? You expect something different can happen, or it's just a slight modification? I don't know if the circles are different or you impose a rotation instead of the.
Okay. I do not hear you very well.
Okay. I mean, the fact that you're not hearing, sorry.
Yes, okay.
Okay. The fact that you are considering your surface to be constrained to these two circles at the top and at the bottom,
Okay.
it's physical, you can change this condition, or it's just because otherwise you will have a trivial solution and that's it.
Okay. No, this was just a choice
Mm.
that we did because in the works from which we started, so in these two works, this was a basic configuration that was treated, and also because when c is equal to 0, you already know the basic solution, so you already know what happened, and so you can say, okay, I know that when c is equal to 0, the basic solution is or the catenode or the two disks, and when c tends to infinity, you know that the admissible thing would be a cylinder, so you know, okay, it will be something in the middle. For example, in the first case, you have something that is between the catenoid and the cylinder. In general, this can be totally changed. So it could be another thing, not just to change the geometry, but also, for example, to take these two circles and made it, for example, elastic. So what happens when you have a deformable boundary and this deformable surface attaches with a deformable boundary? So it would be another interesting problem. So I think you can take really a variety of shapes. It's not trivial.
Okay, thank you very much. Are there other questions? Okay, if it is not the case, we can thank Chiara again.
Thank you.
And thank you very much all for being here. And I guess, Marco, you can stop the recording.
Yes, I will.